Hello everyone. We'll wait for some time till everyone joins and then we'll start the session. Hello everyone. Am I audible?
Audible.
Okay. The video is also visible, right?
Yes, ma'am.
Okay. So welcome everyone. This is the fourth week of TA session for drug delivery principles and engineering. So we'll start today's session. I'm going to share my screen now. Is my screen visible to everyone? Can someone
Yes,
unmute
madam.
and let me know? Okay. Is it visible to
Yes, yes.
everyone?
Yes, madam.
Okay. Okay. So, welcome to the fourth TA session for Drug Delivery Principles and Engineering. Uh, Before we proceed, this entire session is recorded and will be uploaded on YouTube. And this presentation will also be shared with you over Google Drive. So this week, the topics that were discussed were nano and microparticles, different types of different techniques to prepare nano and microparticles, liposomes, dendrimers, and their applications was discussed this week. So anyone has any doubt from the lectures? If not, we'll straight away move to the question answers. Okay, I guess we'll move on to the assignments directly. So this is the first question for today's assignment. What is proton sponge effect? You have to choose two options that are correct. Particles carry secondary or tertiary amines, which helps in escaping endosomal and lysosomal vesicles inside the cells. Phenomenon which leads to osmotic swelling and bursting of vesicles. Particles act as sponges for electrons. The phenomena where particles carrying positively charged moieties neutralize free radical moieties in an extracellular environment. The phenomena of gaining positive charge during endosomal transport. A sponge soaks up all protons in the vicinity. A phenomena of gaining negative charge during endosomal transport. Anyone would like to answer?
First two.
First two.
Option A and B.
Okay. That is, particles carry secondary and tertiary amines, and it is a phenomenon that leads to osmotic swelling and bursting of vesicles. Anyone else has any other option as their answer? Anyone else would like to answer? It would be better if you guys unmute and let me know because I won't be
Answer
able to see chat. Yes.
Ma'am, screen is not visible,
answer
ma'am.
A and B, ma'am.
Okay. Okay, I'll share my screen again. Okay, is it visible now?
Now it is visible.
Yeah.
Sorry?
Answer A and B, ma'am.
Okay. But the screen is visible now, right?
Yes,
Yeah,
ma'am.
ma'am. You can
Okay.
able to
Yes,
see.
ma'am.
Yes, yes. Okay, you guys were correct. The answer is A and B. The first option that is correct is particles carry secondary or tertiary amines, which helps in escaping endosomal and lysosomal vesicles inside the cells, and phenomena which leads to osmotic swelling and bursting of vesicles. So particles are basically taken through endocytosis and they get localized in endosomes and lysosomes where the environment is very harsh. And to escape this mechanism, proton sponge effect is used. And in this, particles are designed to carry secondary or tertiary amines that buffers the pH of endosomes. So these secondary and tertiary amines will attract more positively charged ions. So what will happen is more charge will be accumulated inside the endosome as compared to the outside, and therefore there will be uh, that will lead to osmosis, and more and more diffusion of water will take place that will lead to osmotic swelling and bursting of vesicles. So polyethylene imine is the widely used polymer for this phenomena, and conjugation of peptides that can create pores in endosomal membrane can also be used. However, the maximum reported efficacy for endosomal escape is less than 10%. But the design of particles with secondary or tertiary amines is a good strategy to escape the endosomal or lysosomal vesicles. We'll move on to the next question. Which one is not correct about dendrimers? They are tree-like polymers branching out from a central core and subdividing into hierarchical branching. They are generally not more than 100 nanometer in size, very dense surface surrounding a relatively hollow core. They have very high molecular weight. The entire structure can be divided into generations of shells. Branch density increases with each generation. The size of dendrimer depends upon the number of generations, and they are generally more than 100 nanometer in size. Which of the following options is not correct?
Last option.
Okay.
Option B, ma'am.
Okay. Anyone else? Option B.
Option B.
Okay. Anyone else has any other option as their answer?
Ma'am, please discuss first answer, ma'am.
Sorry?
Please discuss first answer, ma'am, one more time.
I'm sorry. Can you speak again? Last option. Please discuss first answer. Okay. Okay. So the first question was proton sponge effect. So we had to choose two correct options. That is the correct options were particles carry secondary or tertiary amines, which helps in escaping endosomal and lysosomal vesicles inside the cells, and phenomena which leads to osmotic swelling and bursting of vesicles. So basically what is happening is proton sponge effect is used when, so particles, when we are delivering the particles inside the body, the cells, basically immune cells mostly take up these particles. Now they are in the cytoplasm, but since these are taken through endocytosis, a vesicle will form inside it, which is basically endosomal, and if it fuses with the lysosome, it's inside a lysosomal vesicles. So if our particle enters into a endosomal or lysosomal vesicles, it won't be able to release the drug, and if we are delivering a peptide or something, it might get degraded inside those vesicles. So we need a strategy to escape from these vesicles, and that is where comes the proton sponge effect. So secondary or tertiary amines, if we design our particles in such a way that the particles have secondary and tertiary amines, they'll have positively charged, they'll attract more hydrogen ions towards them, and this will lead to a imbalance in the ions inside the vesicles and outside the vesicles. So it will lead to more osmosis of more diffusion of water molecules inside the vesicles. That will basically lead to osmotic swelling and bursting of the vesicles. That is why the two options, there is secondary and tertiary amines, helps in escaping endosomal vesicle, is correct, as well as the phenomenon which leads to osmotic swelling and bursting of vesicles. Okay, now for the next question. Some of you had answered last option and second option. Anyone else would like to answer? Which of these following which of the following is not correct for dendrimers? Am I audible?
Yes, ma'am.
Okay. Yes, so anybody else has any other answer? Which option is not correct about dendrimers? Option B. Okay. Okay, so the answer is they are generally more than 100 nanometer in size. This option is wrong. Those who were saying they are generally not more than 100 nanometer size, this is actually true about dendrimers. They are not more than 100 nanometer in size. So dendrimers are these uh, polymers with that has several branches coming out from a central core, and they are not more than 15 nanometer in size, high molecular weight, very dense surface surrounding a relatively hollow core, and surface may consist of acids or amines, and these branches, the number of branches, so each shell, these shells are called as generations, and the branching density increases with each generation because that will be more and more branched with each subsequent shell. So they are generally not more than 100 nanometer in size is the correct answer. Now the next question. Ranking the order of clearance of charged molecules, pick the right one. Assume all particles are of same size and below 6 nanometer. Negatively charged nanoparticles are cleared faster than neutral ones, followed by positively charged nanoparticles, owing mainly to interactions with the GBM. And neutral nanoparticles are cleared faster than positively charged ones, followed by negatively charged nanoparticles, owing mainly to interactions with GBM. Okay, I'll give you guys some time to read the question and then you guys can answer whenever you are ready. You have to rank the order of clearance of charged molecules if all the particles are of same size and below 6 nanometer.
Ma'am, option C.
Okay, positively charged nanoparticles are cleared faster than negatively charged ones, followed by neutral nanoparticles, owing mainly to interactions with GPM. Okay,
Option D, ma'am.
positively charged nanoparticles are cleared faster than neutral ones, followed by negatively. Okay, anyone else would like to answer?
Option 4.
Positively charged, followed by neutral ones, followed by negatively charged. Anybody else has any other answer? Anyone else would like to answer?
Ma'am, fourth option.
Okay. Yes. So those who said fourth option, that is correct. Positively charged nanoparticles are cleared faster than neutral ones, followed by negatively charged particles, owing mainly to interactions with the glomerular glomerular basement membrane. So the endothelial glycocalyx, that is charged layer 1. This is the charge layer 1. There is second charge layer, that is the GBM, and the podocyte glycocalyx, that is the charge layer 3. These are negatively charged and thus make the glomerular filtration of engineered nanoparticles charge dependent. So the positively charged particles will quickly interact with them, and then they'll quickly cross all these three layers of charge and enter for clearance. That will be followed by neutral particles, whereas the negative particles, they will suffer severe repulsion from the basement membrane, and then uh, so this is why the positively charged particles will be cleared faster than followed by neutral and then negatively charged, given they are all of the same size. Now for the next question, which one of the following is correct with regard to elasticity of particles? Stiffer particles with high modulus of elasticity can circulate for longer duration since they cannot be degraded easily. Low modulus particles can circulate longer as they can squeeze through tissues, avoiding uptake by immune cells. If the particles are highly elastic, they can escape phagocytosis irrespective of their size, and elasticity has no role with respect to phagocytosis. Which of the option is correct?
Option B, ma'am.
Sorry, first and
Second option.
you have to select one option here. Which of one of the following is correct? Only one option is correct.
Second option, ma'am.
Okay,
Second option.
okay. Anyone else has any other option as their answer? Option B. Anyone else would like to answer? Okay, the second option is indeed correct. Low modulus particles can circulate longer as they can squeeze through tissues, avoiding uptake by immune cells. So elasticity has been reported to have a profound effect in circulation times in blood. The best known examples is RBCs, which are known to circulate in blood for months. For low modulus, larger particles were able to circulate in blood longer compared with their smaller counterparts. And this is how particles are able to squeeze through the fenestrations in spleen and they avoid uptake by the immune cells. That is why they are able to circulate for a longer duration as compared to a stiffer or higher modulus particles. Now the next question. Pegylation of nanoparticle is a common practice to evade uptake by phagocytic cells. Which one of the conformations of PEG is preferred to maximize this effect? Brush conformation, mushroom conformation, orientation doesn't matter, triangular orientation, circular orientation, or cubical orientation. Which conformation of PEG is preferred to maximize the effect of evading uptake by phagocytic cells?
Option A.
Brush conformation. Okay.
A option.
Okay. Anyone else? Anyone else would like to answer? Which conformation of PEG is preferred to maximize the effect of evading uptake by phagocytic cells?
Option B, ma'am. Brush.
That is option A.
Yeah. Sorry, ma'am. Option A. Brush mushrooms. Brush. Brush confirmation.
Okay. Okay, so brush conformation is actually the correct answer. It is considered better because, as you can see here, they are able to prevent the proteins and those things from coming close to the particles. Whereas in case of mushroom conformation, there is some gap between the peg chains that leads to protein interaction with the particles. And as soon as the proteins interact with the particles, they'll attract more and more immune cells, and that will lead to phagocytosis. So that's why brush conformation helps in evading the phagocytosis of particles. Now, the next question, which is the working principle behind enhanced permeation and retention effect? You have to select two options: excessive nitrogen in the vicinity, positive pressure between vasculature. Okay, which is the working principle behind enhanced permeation and retention effect? Excessive nitrogen in the vicinity, positive pressure between vasculature and intratumoral environment allows flow of particles from vasculature to tumor tissue. P53 mutation causes that protein to bind more tightly to the particles. Oncogenic mutation increases the tension of cells to nanoparticles. Faulty lymphatic clearance of particles from intratumoral environment. Oncogenic mutation increases repulsion of cells to nanoparticles. What is the working principle of enhanced permeation and retention effect?
Fourth and fifth.
Fourth option.
Fourth and fifth.
Oncogenic mutation increases attention of cells to nanoparticles, and faulty lymphatic clearance of particles from intratumoral environment. Okay. Anyone else? Anybody else would like to answer this question? What is the working principle behind enhanced permeation and retention, or EPR?
Option 2 and 5.
Option, sorry, yeah, option 2 and 5. Okay. Anybody else has any other option as their answer? Okay. So those who I think only one person answered the second and fifth option. That is correct. Positive pressure between vasculature and intratumoral environment allows flow of particles from vasculature to tumor tissue, and the faulty lymphatic clearance of particles from intratumoral environment. So what is first enhanced permeation and retention? So as you can see here, this is a blood vessel and this is a tumor environment. So when a particle flows through this blood vessels, the the cells that are formed near the tumor tissue, they are mostly formed very rapidly and they are not properly organized. So there are a lot of gaps between them during organization. That is what leads to entry of the particles through these leaky vessels into the tumor. This is called enhanced permeation, permeability through the membrane, and retention in the tumor environment. So that and this positive pressure between the vasculature and the intratumoral environment actually allows the flow of particles from the vasculature to the tumor tissue, and the lymphatics is there is faulty lymphatic clearance from particles because the tumor tissues are not very well organized and they have faulty lymphatic systems. They are not able to clear these particles, which is why particles are able to reside more inside the tumor environment. So these two options will be correct. Sure, I'll repeat once again from 1 to 5 when this is completed. Okay, now let's move on to the next question. Okay, so the next question is, which of the following methods can be used to measure size of nanoparticles? You have to select two options. Options are X-ray diffraction, dynamic light scattering, atomic force microscopy, gene transduction, ballistic gene gun mediated transfer. Which of the following methods can be used to measure size of nanoparticles?
Second and third option.
Second and third option. Okay. Anyone else?
Ma'am, first and second.
First and second. Okay.
First and third, ma'am.
First and third.
Option B and option C, ma'am.
Okay. Anyone else would like to answer? Yes, so option B and option C is correct. That is dynamic light scattering and atomic force microscopy. So qualitatively, microscopic techniques can such as atomic force microscopy or scanning electron microscope. Basically, electron microscopic techniques can be used for particle size and shape. And for quantitative Coulter counting or light scattering techniques such as dynamic light scattering, DLS, can be used. This gives a distribution of diameters from which number average, weight average, volume average, and volume average sizes can be calculated. Okay, so next question. Which one of these is not an advantage of nano and micro particles? The options are injectable, no need for surgical implantation, can elicit inflammatory reactions in host, possible way of delivering large hydrophilic molecules inside cells, Particles can be adapted for targeted delivery to cells and tissues, improving the stability of the drug in vivo.
Second option, ma'am.
Okay, can elicit inflammatory reactions in host.
Option B, ma'am.
Okay,
Injectable, ma'am. First option, ma'am.
first option. Okay, second option. Anyone else? What is not an advantage of nano and microparticles? Okay, so those who said that it can elicit inflammatory reaction in host, this is basically not an advantage. This is a disadvantage of nano and microparticles. Injectable, well, most of the nano and microparticles are injectable. That is one major advantage of particles. So there is no need for surgical implantation. Possible way of delivering large hydrophilic molecules. Particles can be adapted for targeted delivery to cells and tissues, improving the stability of the drug in vivo. These are also advantages of the nano and microparticles. So let's move on to the next question. Which one of the following?
So answer, ma'am.
Sorry?
So answer one more time, ma'am.
Answer is can elicit inflammatory reactions in host.
Ma'am, meaning of the word elicit means
Elicit means it will try to provoke an inflammatory reaction in host. Try to
okay,
create inflammatory reactions in host.
okay.
Okay, we'll move on to the next question. Which one of the following parameters does not affect microparticle synthesis using double emulsion method? Which of the following does not affect microparticle synthesis?
None
So,
of the above.
sorry,
Last option, ma'am.
none of the above. Okay. Anyone else?
None of the above.
Last option. Okay. Anyone else has any other answer? Which of the following parameters does not affect microparticle synthesis using double emulsion method? Okay, you guys are all correct. It is none of the above. So this is basically how a double emulsion particle is formed. First, uh, it can be water, oil, water double emulsion process. So in this, PLGA or the polymer is in solvent first, and then aqueous drug solution with water is then poured into the PLGA in the solvent. And then this will lead to, and then when we homogenize this solution, this will lead to polymer in organic phase and drug in water phase will form small micelles. And then again we pour them into an aqueous solution of PVA. So this will lead to a double coating of these particles. So inside there will be an aqueous layer followed by organic polymer layer followed by water layer. So the drug encapsulated microparticles will be something like this. And all these parameters that were mentioned above, polymer type and molecular weight, polymer concentration in the oil phase, type of drug and method of incorporation, organic solvent used and polymer solubility, type and amount of surfactant in the external phase, internal aqueous phase or organic solvent ratio, rate of stirring and type of mechanical force, evaporation rate, temperature, pressure, extraction rate, all these parameters will affect formation of these particles. Okay, we have reached the last question. So the last is a numerical type question. A core shell type nanoparticle is synthesized. The radius of the core is 2 nanometer, whereas that of the whole particle is 5 nanometer. What is the ratio of volumes of the core to shell?
6.4, ma'am.
Sorry,
6.4, ma'am.
6.4.
No.
Okay. It is asking the ratio of volumes of core to the shell. Anyone else has any other answer?
Option 8, sorry, answer 8, ma'am.
8. Okay. Anybody else? Anyone else has any other answer other than 6.4 and 8?
Ma'am, 0.064.
Okay. Anyone else? So 0.064 is the correct answer. So if such questions are there, if your answer lies between the range of 0.05 to 0.07, it will be accepted as the correct answer.
But he asking in ratio, ma'am.
Sorry?
But he is asking in ratio, ma'am.
Yeah, this is the ratio only. So radius of, okay, let's solve this and then you let me know what your doubt is. So radius of core, it says 2 nanometer. Radius of whole particle is 5 nanometer. So the ratio of the volumes would be volume of core divided by volume of shell. That is 4 by 3 pi r1 cube by 4 by 3 pi r2 cube. So basically this is r1 cube by r2 cube, that is 8 upon 125. This is the ratio, which is 8 by 125. But since it is asking for a number, you have to convert it into decimal, that is 0.064. Yes, now what was your doubt again?
Yes. My doubt is reacting in a ratio, ma'am. So I think giving answer in ratio, ma'am, 6.4, I think.
That is percentage. If you multiply by 100, that will be a percentage. Ratio is basically division of that volume of core to volume of shell.
Okay. Sure, ma'am. Thank you.
But madam, while putting the answer, na,
Hmm.
only what we can say integer they are taking. 0.06 or point something value is not taken by that particular form.
So I think the answer will vary from question to question. In some cases, they'll ask for only integer. In that case, you don't have to put decimal numbers or fractions. You can only enter
Mm.
integers.
But in this case, I have tried to write 0.067, but was not possible.
Uh, what question was that?
Same question.
The same question
Yesterday
was.
I tried to yes, yesterday I tried to solve it
Hmm.
and try to write the answer 0.06, but I was not able to write that answer.
Okay, I'll ask
Hmm.
I'll ask and let you know what is the problem is.
Okay,
Did
thank you.
others also face the same problem?
I am, ma'am. Same problem, ma'am. The decimals is not getting to write. Only the
Okay,
single numericals we are able to write. We are not getting decimals to write.
I see. So did you guys try to enter zero also? Like,
Yes, ma'am.
okay, okay. And you still haven't gotten the correct answer, right?
Right.
Ma'am, I was able to enter the answer.
Okay. The entire answer 0.064.
Yes, ma'am.
Okay. Then maybe some technical issue with other others, I guess.
We'll try this.
I'll still check and let you know what the problem might be. And we can allow decimal numbers also as answers from next time
Yes,
onwards.
ma'am. Thank you.
Okay, so those who joined late will start again with question 1. Anybody else? Anybody has any doubt in all the questions that we discussed till now? So that otherwise we'll repeat again. Okay, I guess we'll repeat from question 1. So the first question was, what is proton sponge effect? You have to select two options that is correct. Particles carry secondary or tertiary amines which helps in escaping endosomal and lysosomal vesicles inside the cells. Particles which leads to osmotic swelling and bursting of vesicles. Particles act as sponges for electrons, the phenomena where particles carrying positively charged moieties neutralize free radical moieties in an extracellular environment. The phenomena of gaining positive charge during endosomal transport. A sponge soaks up all protons in the vicinity. And the phenomena of gaining negative charge during endosomal transport. So the first two options are correct. Particles carry secondary and tertiary amines which helps in escaping endosomal and lysosomal vesicles inside the cells, and this phenomenon leads to osmotic swelling and bursting of vesicles. So proton sponge effect is basically a strategy to escape from the endosome and lysosomes wherein we can design the particles such as they have secondary and tertiary amines that will lead to more ions inside the vesicles as compared to the outside. This will attract more water, diffusion of water into the vesicles, and this would lead to osmotic swelling and bursting of vesicles. The next question was, which one is not correct about dendrimers? They are tree-like polymers branching out. Am I audible, guys? Hello?
Yes, ma'am.
Okay. So the second question, which one is not correct about dendrimers? They are tree-like polymers branching out from a central core and subdividing into hierarchical branching. They are generally not more than 100 nanometer in size, very dense surface surrounding a relatively hollow core. They have very high molecular weight. The entire structure can be divided into generations of shells. Branch density increases with each generation. The size of dendrimer depends on the number of generations. They are generally more than 100 nanometer in size. So the option they are generally more than 100 nanometer in size is actually not correct. They are usually not more than 15 nanometer in size. And the rest of the options were also correct. They have high molecular weight, branching, etc. etc. Now, the next question was ranking the order of clearance of charged molecules. We have to pick the right one, assuming that all the particles are of same size and below 6 nanometer. So the correct option would be positively charged. The third option, that is positively charged nanoparticles are cleared fast. Sorry, the fourth option, positively charged nanoparticles are cleared faster than neutral ones, followed by negatively charged nanoparticles owing mainly to interactions with the GBM. So there are three layers of charges, the endothelial glycocalyx, that is charge layer 1, and then there is charge layer 2 with the glomerular basement membrane, and then podocyte glycocalyx charge layer 3. All of these are negatively charged. So the positively charged particles interact with this and are quickly cleared away. That is followed by the neutral particles, and then negatively charged particles, they face severe repulsion from these different layers of negative charge. So they are cleared less compared to positive and neutral particles. So the order would be positively charged nanoparticles are cleared faster, followed by neutral, followed by negatively charged nanoparticles. Now the next question, which one of the following is correct with regard to elasticity of particles? Stiffer particles can circulate for longer duration since they cannot be degraded easily. Low modulus particles Low modulus particles can circulate longer as they can squeeze through tissues, avoiding uptake by immune cells. If the particles are highly elastic, they can escape phagocytosis irrespective of their size. And elasticity has no role with respect to phagocytosis. So the correct option would be low modulus particles can circulate longer as they can squeeze through tissues, avoiding uptake by immune cells. The next question was, pegylation of nanoparticle is a common practice to evade uptake by phagocytic cells. Which one of the conformations of PEG is preferred to maximize this effect? Brush, mushroom, orientation doesn't matter, triangular orientation, circular or cubical orientation. So the correct option would be brush conformation. Now, if pegylation is done on a particle, the brush conformation will prevent, there will be very less, the brush conformation will be basically waving in the uh, environment. So they will prevent these proteins from interacting with the core. Whereas the mushrooms, they will have some gap through which the proteins can squeeze in and interact with the particles. So brush conformation is better in preventing protein interaction with the particles that actually leads to further attraction of immune cells and leads to phagocytosis of particles. The next question was, which is the working principle behind enhanced permeation and retention effect? So the option that is positive pressure between vasculature and intratumoral environment allows flow of particles from vasculature to tumor tissue. And the fifth option, that is faulty lymphatic clearance of particles from intratumoral environment, are the correct answers. So EPR, or enhanced permeation and retention effect, is basically when so this is a tumor, and this is the tumor environment, and this is your blood vessels. So the cells that are formed by the tumor or in the nearby regions, they are basically formed, they grow very rapidly, they are not very organized, so that leads to leakage, uh, that leads to very low level of organization. The organization is not very good, that leads to lot of gaps between the cells, and that is why particles are able to easily permeate through these gaps into the tumor tissue or the tumor environment. And since these tumors does not have good lymphatic system, their clearance is faulty, and this leads to more and more accumulation of the particles in the environment. This is what is called enhanced permeation retention, and that is why these two options will be correct. Which of the following methods can be used to measure size of nanoparticles? So dynamic light scattering and atomic force microscopy can be used to measure size of the nanoparticles. So the atomic force microscopy or other microscopic techniques can be used to qualitatively measure the particle size and shape, whereas Coulter counting or dynamic light scattering or other light scattering techniques can be used to quantitatively measure the particle size and shape. The next question is, which one of these is not an advantage of nano and microparticles? Injectable, that is no need for surgical implantation. Injectable, there is no need for surgical implantation, can elicit inflammatory reaction. This is actually not an advantage. Possible way of delivering large hydrophilic molecules. Particles can be adapted for targeted delivery to cells and tissues, and improving the stability of the drug in vivo. Rest all the options are advantages of nano and microparticles. The only disadvantage or not an advantage is can elicit inflammatory reactions in host. The next question is, which one of the following parameters does not affect microparticle synthesis using double emulsion method? Polymer type and molecular weight, polymer concentration in the oil phase, organic solvent used and polymer solubility, type and amount of surfactant in the external phase, internal aqueous phase or organic solvent ratio, rate of steering and type of mechanical force, or none of the above. All the parameters in the above options are correct. So none of the above would be the correct answer here. All the options, all the parameters actually affect formation of microparticles using double emulsion method. And the last question was, a core shell type nanoparticle is synthesized. The radius of the core is 2 nanometer, whereas that of the whole particle is 5 nanometer. What is the ratio of volumes of the core to the shell? So the ratio of volumes of core to the shell would be volume of core divided by volume of shell. And the volume is given by the formula 4 by 3 pi r cube. R1 here would be 2 nanometer for core, and R2 would be 5 nanometer for particle. So basically this is 2 cube upon 5 cube, or 8 by 125, which is equal to 0.064. So the correct answer is 0.064. Okay, now anyone else has any other doubt or wants me to repeat any question or discuss any particular question?
Excuse me, ma'am. Ma'am, for question number 2, what is the correct answer? Is it the last option?
Question number 2.
Yes, ma'am.
Okay, let me check. Which one is not correct? Yes, the last option is correct. They are generally more than 100 nanometers in size. They are not more than 100 nanometer in size. Basically, they are not more than 15 nanometer in size. So this option would be incorrect.
Okay, ma'am. Thank you.
Yeah. Anyone else has any other doubt or wants me to repeat any other question? Anyone has any doubt? Regarding this assignment or previous assignment? You want me to go through the slides once more? Should I just go on with the slides or should I discuss them? Do you want me to discuss them or just go? Okay. Yes, Sadhana.
Good afternoon, ma'am. Good evening, ma'am.
Yes, good evening.
Ma'am, today topic, ma'am.
We actually we just finished discussing everything. But
Okay.
if you want me to go through again, we can go. We'll just wait for 2 more minutes if anybody else wants to join. We can start again.
Okay, ma'am. Thank you, ma'am.
No problem. So nanoparticles and microparticles were basically discussed in the last week, and most of the questions are based on these nanoparticles and microparticles. I guess no one is joining. So we'll go through the questions. I'll quickly discuss all the questions. You can stop me anywhere you want me to, and we can stop and discuss. So first question was, what is proton sponge effect? You have to choose two correct options. So here particles carry secondary or tertiary amines which helps in escaping endosomal and lysosomal vesicles inside the cells. Phenomena which leads to osmotic swelling and bursting of vesicles. These two are the correct options. So proton sponge effect is basically escaping mechanism from endosomal or lysosomal vesicles. So we can design our particles in such a way that they have secondary or tertiary amines, and this leads to more and more ion accumulation inside the vesicles as compared to outside the vesicles. This leads to there is an imbalance between inside and in the amount of ion inside the cell compared to the outside. So this leads to more diffusion of water into the cells that leads to osmotic swelling and bursting of vesicles that frees the particles to the outside. So this is what proton sponge effect is. Now the next question was which one is not correct about dendrimers? Am I audible?